Hi, welcome to videos on log filters again. So in this we'll see second order RC high pass filter. So this is a general transfer function of a second order filter. So having the denominator of the expression indicating the pole position and the numerator indicating the possible zero position. So let us see what is a second order high pass filter transfer function. So this is our general transfer function. If you can see now, this general transfer function has reduced to this particular transfer function for a high pass filter. You can see a denominator remains same as that of the general transfer function. In the numerator, we don't have the coefficients of s and s power 0. So we have only the coefficient of s square, that is a2 into s square is the only numerator term we have, indicating that we have only two poles at the origin. So repeating poles at the origin, and of course we have the zeros located at on the left hand side of the S plane, which are complex in nature. So let us see the pole zero position of this. So if you can see here, looking at the denominator of the transfer function, the poles are located at a distance omega naught by 2q away from the imaginary axis. They are complex in nature, and you can see there are two repeating poles at the origin of S plane, so which is a representation of this S square term on the numerator of the transfer function. This S square indicates repeating poles at the origin, repeating zeros at the origin of the S plane. Of course, this indicates the poles are located on the left hand side, which are complex in nature. Because of this transfer function, we will going to have a Bode plot whose initial slope is plus 40 dB per decade starting from the origin frequency itself, that is starting from DC itself, and it is keep increasing with a slope of plus 40 dB per decade. So whenever we have the omega, the poles coming into picture, the slope becomes 0. So this is an overshoot response that depends on the value of Q and omega naught. So that we'll see in the coming slides. So this is the Bode plot of the high pass filter. Initially slope is plus 40 dB per decade, and then finally it becomes 0 dB per decade after it crosses the cutoff frequency of the filter. So this is the practical implementation of high pass filter using op-amp circuit. If you can see, there are two RC networks which will constitute second order filter. And of course, this gain with gain expression as 1 plus RF by R1 will control the overshoot of the response. Let us see the transfer function of this particular high pass filter circuit. So as we did in low pass filter circuit also, we have identified different circuit variables, like Vin is a independent variable, and along with that we have so many dependent variables, two currents I1, I2. Of course, there are three voltages V1, V2 and V0, which are the dependent parameters. We are trying to write the expression for all dependent parameters. If you can see here, the expression for I1 happens to be the potential difference between the capacitor C divided by the reactance. Since it is divided by, it will be Vin minus of V1 into CFS. So similarly, the current flowing through this resistor is the potential difference of across this R, which is equal to V1 minus of V0 minus of V0. So if you want to write the expression for V1, that minus will go on to the right hand side, and we're going to get this as the expression for the V1, that is the drop across this resistor plus V0 happens to be V1. Similarly, we can write it for I2, V2 and V0. So V0 is the output voltage as a function of V2, which is gain times V2 here. So here the gain is 1 plus RF by R1. You can see this is 1 plus RF by R1. So in the denominator we have R1 here. Okay, now using that circuit parameters, we can write a signal flow graph for that particular circuit diagram. So this is how the signal flow graph looks like for different variables Vin, I1, V1, I2, V2 and then V0. So this is constructed looking at these equations. We have I1, V1, I2, V2 and V0. So that will give you this particular signal flow graph. Finding the gain of this particular signal flow graph using Mason's gain rule, we will have the forward path as if you can see the multiplication of all these forward gains, that is R, CS, R, plus we have this CS into R and CS into R, that is what is this, we have two terms of R into CS. Of course we have a gain of AF, and we have 1, 2, 3, 4 individual loops. You can see 1, 2, 3, and of course this is negative sign because we have a positive feedback which is CS R into AF. This is a positive feedback. The remaining 3 loops are negative feedbacks. You can see that's why it has a plus term. And we have this and this, which are non-touching loops. So 2 non-touching loops. We want to have the gain product of those two non-touching loops. So this will reduce to equation which is of this sort. So making the quotients of grouping all the terms. So we'll end up with this as a transfer function. So simplifying this particular transfer function, we'll end up with S square into AF divided by S square plus 3 minus AF into S by RC plus 1 over RC whole square. So this is the expression for the circuit diagram of a second order high pass filter. So we will try to compare this with the generalized expression, try to get the value of Q, omega naught and all those things. Here this is the generalized transfer function for a second order high pass filter. This is the expression, the transfer function for this particular circuit. If we compare these two, so we are going to get the quality factor of the poles as Q is equal to 1 over 3 minus AD. The cutoff frequency in terms of radian is radian per second is 1 over RC, or in terms of hertz it will be 1 over 2 pi RC. The op-amp closed loop gain happens to be 1 plus RF by R1. So this is what is the circuit. 1 plus RF by R1 happens to be the gain of this circuit. We know that depending the value of Q, the frequency response of the system will have a maximally flat response, it will be a poor response, it will be poor flatness, or it will be a overshoot. So that's what we are seeing here. So this is the comparison between Q and AV values. So we know that the Q and AV are related using this expression. If Q happens to be, suppose Q has to be less than 0.7, then AV should be less than 1.56. So that's what we have here. So that type of gain will going to have a poor flatness, and if the gain is exactly equal to 1.56, we'll have a maximally flat response. Similarly, for overshoot, we have to have more than 1.56. So let us analyze the working of a high pass filter using 20 sim. So let us take the example of omega naught, which is 1000 radian per second. So 1 over RC so and so. Let us see the maximally flat response for which AV happens to be 1.56. So the transfer function has to be this while analyzing the 20 sim simulator. So let us go to 20 sim simulator, edit the transfer function as it is given here, and then try to see what is the Bode plot as well as the pole zero plots. Okay, let us edit the transfer function of this particular high pass filter. So let me see what is this. Okay, this is the transfer function of the high pass filter for a maximally flat response. So which happens to be 1.56 square, and of course we don't have any other terms. For which, okay, let us type here as 1.586. There is a space with 0 and then one more space with 0. This indicates that okay, this is 1.56 into S square plus 0 plus 0, which is what is the representation of this particular term. So coming to denominator, we have S square, which is the quotient of S square is 1, whereas the quotient of S power 1 is 1401. Let me edit this to, this is 1410. Of course this is the space, and this is followed by 1 over RC whole square. So we are done with the transfer function. If you can see the pole zero plot, this is the pole zero plot. You can see there are repeating zeros at the origin. We have 2 poles located which are complex in nature. That's what we saw in the slides also. So let us see the Bode plot of this. So Bode plot of this should yield a maximally flat response. You can see now this is the response of the system on the Bode plot. You can see now it is having a slope of plus 40 dB per decade initially, and then it becomes flat, and the phase is plus 180 degree initially, and then it becomes 0 degree. So at exactly cutoff frequency of 1000 radian per second, the phase will be plus 90 degree. That we can verify here. So let me just move this so that just keep on observing this x and y values. When the x value is 1000, this becomes 90 degree, indicating that at cutoff frequency phase is, you can see it's almost there at 1008. This is 89.2. Suppose if you calculate this with 1000, this will become 90 degree. So when the frequency is very less, it is almost 180 degree. The frequency is very high, you can see it's almost 0 degree. So correspondingly, so we will have the magnitude plot, so which will be 3 dB down at when I say 3 dB down, you can see here it is, you have 4 dBs here. So at exactly 1000 radian per second, it will be 3 dB, 1 dB. So 4 minus 3 happens to be 1 dB. So just tendency here, this is almost equal to 1 dB. The corresponding frequency would be 1000. You can see it's almost there. So this is almost 1 dB. So that is 3 dB down. So let us change the transfer function to different pore flatness and the overshoot, and then see the responses. You can see this is a transfer function for overshoot response. So you can see this is 2.5 s square, and this is s square plus 500 s and 1000 square. So this give again repeating zeros at the origin. I mean, of course, the poles are moved close to the imaginary axis. If you can see the Bode plot, you can see there is an overshoot. So there is an overshoot, and of course the same phase is equal to initially 40 dB per decade, phase is 90 degree at cutoff frequency. All those things remain same. So let us see the pore flatness response for a reduced gain. Next we have the pore flat response. So where the AV is equal to 1.1, you can see this is at 1.1, and we have it as s square plus 1900 s into 1000 square. So that's what you have here. So let us see the time Bode plot as well as the pole zero plot. You can see this is the pole zero plot. You can see this is too far away from the imaginary axis. We have the repeating zeros at the origin. The corresponding Bode plot will show you the pore flat response. You can see the flatness is not very good here, so it has bit reduced. So let me just redo it. So this is how the Bode plot for a gain of 1.1 will look like. So for this will have a very poor response. So we'll see that LT Spice simulation also for this high pass filter for different gains. So let us go to, so this is the high pass filter. You can see now we are changing the value of R to 586, 1500 and 100, corresponds to a gain of maximally flat, overshoot and a pore flatness response. Let me run this. So this is the transfer function what we are getting. Let me just close this. So let me close this also. This is the transfer function here. So this is the transfer function what we are looking at. You can see we have three plots. One corresponds to overshoot, one corresponds to maximally flat response, and the green one is for pore response. So you can see this is having a slope of plus 40 dB per decade. So that can be seen by placing two cursors at 1 decade difference. Let me just do that. If you can carefully observe, we have placed two cursor number 2 and 1. So one is at 40 Hz and the other is at 391 Hz. So the ratio of the frequency is almost equal to 10. If you can see, the difference in the gain is almost 39.08. So ideally it should be 40 dB per decade. We have almost close to 40 dB per decade. So this is how the frequency response of the high pass filter changes as the gain changes. This is for gain more than 1.56, this is for exactly 1.56, and this is for less than 1.56. So here the gain is 2.5, here gain is 1.1, here the gain is exactly 1.56. So this blue one corresponds to maximally flat response. So this way we can do the simulation.